Alright everybody, so we're almost finished with this unit. We are done with all the content, so this last couple of video lectures that you have before you go in and do problems in class will actually just be more practice. So we've been practicing problems in class. I suggest you to do the end of practice problems, and as an incentive they're extra credit, so you can get extra credit onto your classwork. But even if you don't want to do them as extra credit at the time that they're due, you can still do them. And so I'm going to actually practice a problem. I'm going to do some practice problems with you as your lecture video. So I'm going to go to our textbook, and it should open on chapter 8 or 9, because as you guys are reading the textbook, I read the textbook alongside you, and I do all your assignments alongside you, just to kind of model that behavior with you. So if I go in to this, I'll go to integrated problems. I was actually already there, and I'm going to just randomly pick a problem. Let's do 94. So I'm going to copy the screen so I can write on my screen, and so I'm going to do this problem. So on this particular problem, it says that we start off with our starting material, compound Y, and its formula is C7H12. So you can calculate the HDI if you want to. I know that one of the products, it says if you treat Y with HBr and peroxide, it will make that, which means there has to be at least a double bond there that does a anti-Markovnikov addition. And so we can prove that by NMR, and I'll actually do that with you guys just as a practice, even though the question doesn't ask that. We can calculate HDI, or if you remember the formula for alkanes, so cyclic alkanes, it's like an alkene. So if you have a double bond and a ring, you should have an HDI of 2. So we're just going to check that. So when I have 7 carbons, I should have 2 times 7 plus 2 number of hydrogens, and that will give me 16. So I'm actually lacking 2 pairs, which is an HDI of 2. So one of those is accounted for by the ring, and one is accounted for by the double bond. But we didn't actually really need that, because we knew that that's the case. Now, the second part of the what I have to do is, since I know that in the presence of HBr and peroxide, this particular molecule is going to give us a anti-Markovnikov, meaning that we're going to add the bromine and the anti-Markovnikov. So to think backwards, if this bromine is added in the anti-Markovnikov, the double bond had to originally be there. That's the only choice that we have, and that would have been the anti-Markovnikov position. So my starting material had to be this. Now, when I draw the reaction of that, it's HBr plus our peroxide, so it can be any kind of peroxide. It's usually actually not H2O2. Should just do ROOR. That's actually more common, and that gives us this compound. So the second part of the problem then says, knowing what compound Y is, now we're going to do ozonolysis. So let's do that. So our trick for ozonolysis is that you split apart the double bond. So split, snip it. Because this is just one carbon here, I'm going to put the hydrogens on to make it more clear, and then we add our oxygens. So these are the 2 products. So this is called cyclohexanone, and remember, I don't need you to know the names of ketones yet, or aldehydes yet. will eventually need to know them.
Right.
And this is formaldehyde, so I'll turn it around.
Oklahoma, he's pitching his business experience. He was in management at McDonald's before he was elected to the House.
So let's do another problem. So I'm going to randomly pick. Again, I'm randomly picking these problems. So one aspect of the previous question that you just had that I mentioned, it wasn't a part of the question, but is relevant to a test question that you have that's going to ask you to use NMR to determine what mechanism to draw. Now, you're not going to have to draw this one with the peroxide yet because we haven't learned that until the next unit, but the same thing could apply with, for instance, comparing oxymercuration, demercuration with hydroboration, oxidation mechanisms, because they give you the same product except one is Markovnikov, one is anti-Markovnikov. So that's a good option of comparison. I could be comparing syndiol or antidiol, although with NMR, that's not something that you know quite yet how to do. So this is a good example of where I could take NMR to answer like which mechanism would undergo something, but a step further would be ones that you could have two different things and then draw a mechanism, and that's like the question on your test. So what am I looking for on these two molecules? So in the beginning, in terms of proton NMR, we should see alkyl groups on the proton NMR for the starting material somewhere between about 1 and 2 ppm, and the hydrogens nearest to the pi bond, so these hydrogens here and the same on these sides, are probably the things that are closest to the 2. Everything else, and actually I wouldn't say 0, it's more like a little bit over 0 to 2 ppm. Now, once we add our halide onto the molecule, the hydrogens nearest to these hydrogens should start approaching more of the 2 to 4 ppm, probably like 3.5-ish, right? So that's one thing to look forward to. So the hydrogens closest should be there. On the second molecule, there are no hydrogens that are directly attached to the carbon with the halogen. So all of these, again, they're close, but they're probably closer to the 2 ppm. So this would be closer to maybe 3 to 3.5. These hydrogens would be closer to 2 because they're not directly attached. Second thing that I would be looking for in NMR is that we should see that because there's one hydrogen here, these hydrogens only have one neighbor, so we should get a doublet. Whereas these hydrogens over here have no neighboring hydrogens. There's no neighboring hydrogens over here, so it should be a singlet. So what you'll see on the NMR is exactly that. You will see on this NMR, there should be a doublet present. The second NMR has no doublets. So we won't be seeing a doublet. Whereas this one should have a singlet, and the top one doesn't. So those are some characteristic things. Now we could predict the whole NMR, but what I would do is look at your molecule. Do you see some characteristic things that you can see, and then you can go ahead and match. So then once I got my NMR, I can then see, oh, did I see a doublet? Well, the first one, the anti-Markovnikov, would have a doublet because this hydrogen I'm going to label A and these B. These would match very well onto the NMR because this would give me B. It would integrate for 2 hydrogens and it would only have one neighbor, which its neighbor is A. Whereas this one, you would see a singlet and the top one doesn't have a singlet. So that's a good way of trying to solve these kinds of problems when you see them, is look at what is characteristically different that could give us a multiplicity difference, could give us an integration difference, could give us a shift difference, and this is a good example of one. I would practice these. There's a couple of examples from class. There's also examples in your textbook that you could try, or you could make up a problem, right? So you could say, let's try this with oxymercuration, demercuration, which is Markovnikov, and brown oxidation, which is hydroboration oxidation. Just try an alkene predict what would you see on the NMR. That's a good practice. All right, let's, how about we do 95? Okay, so here we have an epoxide, and we know that epoxides are not stable under acidic conditions. They get protonated to make that oxygen a better leaving group from one side of the molecule, and then they get attacked. So this is my product, and it's asking me to predict what the mechanism is. So I know that under acidic conditions, so I'm going to draw my H3O plus. You could draw it from sulfuric acid directly, it's fine. And then we draw in our lone pairs, right? Because we always draw from lone pairs. Take away our proton, give it to the oxygen. And I'm just going to put R here for now. I'm going to use that later, but just to give me some space. Now, this makes this oxygen a better leaving group, so it will leave one side of the molecule. So now is the time that I am concerned about the rest of my molecules. I'm going to draw that in because that alcohol is going to behave like a nucleophile. It is a weak nucleophile, and we talked about nucleophiles attacking the protonated epoxides because they're easier to attack. And since my stereochemistry here is a wedge, so that's going to kind of force my molecule to be attacking from underneath the epoxide that's going on the wedge. Since the wedges are coming towards me, the epoxide has to come from underneath it. So it's going to come underneath it, attacking that carbon, opening the oxygen.
That was Raphael Cohen, Emma Skye, and Donny Hasseltine. You'll hear more from all of them. Hasseltine was a Marine officer in Iraq after the U.S. campaign that destroyed the city of Fallujah, which he says is the closest parallel to what Israel faces now. Even if you destroy every terrorist in Gaza, you still have a case where you have an area without resources, without jobs, and a very young population. And when you combine this,
so now we get an alcohol on one side, and then on the other side, this oxygen has attacked.
It's not something the U.S. actually ever did very well.
Still has its hydrogen on
He's an
there.
army officer in Iraq. He's now at RAND. You have to begin thinking about these issues.
And so I'm going to count my carbons 1, 2, 3 to just make sure 1, 2, 3. So that's perfect. And I'm going to add my hydrogen, and then water can come in. Remember, it's not going to be the hydrogen sulfide because that's not a good base. So let us actually practice the next problem, but I'm going to need to erase this. So you can always rewind and redraw if you want to. So we're just practicing some problems that illustrate some of the things in this chapter. So in the second part of the video, we'll do more problems. So here the first step is to protonate. So you can use H3O plus, or you can draw out the hydrogen sulfide. It's up to you.
The response to that led to the deaths of hundreds of thousands of Muslims. It led to the US violating human rights, and it did huge damage to America's reputation in the world.
This is the problem with drawing straight out of our textbook, is it'll have a lot of space, but do like that. And so I'm going to draw the result over here.
That's another lesson.
Definitely incorrect. As one starts to fight, as casualties suffer on the other side, then that will create their own difference of benefits. And so that can create a larger, more difficult conflict.
And not just within Israel and the Palestinian territories, says Emma Scott.
Russia and China trying to present themselves as the leaders of the global south, and of course, you're listening to the language coming out of Iran. And so it all becomes, whatever's happening in Gaza becomes a proxy war for something much bigger globally.
And President Biden's embrace of Israel.
So I'm just counting my carbons to make sure I draw the right number of carbons. So this is 5, 4,
Week 7 of the NFL season. But for fans who tuned
and
in
so
yesterday's Bears
that
Raiders
double
game,
bond is nucleophilic, so it can open, but it's going to attack at the most substituted side, because that is the more stable side to attack in terms of the transition state. I open up my brain
He definitely raised
and I count these just because I don't want to make a mistake.
Most important stats, no giveaways.
Agent had flown under most people's radar, in part because over 3,000 students.
last night, though, he captured the hearts of all of Bears
So
Nation as he
I
led
make
Chicago
some
to their
positive,
first
and then I just
victory
put it
of
in
the year.
that.
Here's the call on Fox.
Alright, so notice that the final product has a double bond attached to the ring, and so we have to do an elimination. That's the last step. So we're going to take our water.
Report your NPR comes from this station and from the Joyce
We're going to draw our lone hairs on the water.
Economic mobility for the next generation in the Great Lakes region. Learn more at Joyce.
And we're essentially doing an E1
From the
elimination.
Wallace Foundation, working to develop and share practices that can improve learning and enrichment for young people and the vitality of the
And we
arts
get
for
our
everyone.
final product. Okay, so our next video will practice a couple more problems.